Let's look at this problem. So this is a problem based on electric fields. So if you like, you can pause the video at this time and read the question and try to answer it by yourself. I'm going to read the question and then do it. So there's an electron which is injected horizontally with a speed of 7 times 10 to the power 6. So that is the speed, meters per second, into a uniform electric field that has a strength of 570 newtons per coulombs. So that's the strength of the electric field. As shown in this figure, you can see the uniform electric field is set up by these two parallel plates, and the electric field is pointing in the downward direction. Okay, now this is the electron over here, so it moves horizontally. It is injected at this point with 7 times 10 to the power 6 meters per second, and as a result of the electric field, it's going to curve upward, and then it's going to eject from here with a different speed and making some sort of an angle with the horizontal. So the first part is asking us to find the acceleration of the electron. So the acceleration here, remember, it's a vector quantity, so we need to calculate the direction of the acceleration as well as its magnitude. Now it's also given that we can neglect gravitational effects because the electron has a mass. You can see the mass is given here. It's a very tiny mass, however still it has some mass. But the question is saying that simply ignore gravitational effects for the electron when calculating its acceleration. So let's look at the first part, how to do it. So I'm going to draw the figure. You can see the electric field is pointing downward like this. Then we have the electron somewhere here. Now if the electric field is pointing downward, the electrostatic force acting on the electron is in the opposite direction. So this is the direction of the electrostatic force, F of E. The reason for that is this one. So if you look at the equation, this is the general equation that connects electric field to the electrostatic force. If we specifically apply the electron, then this equation becomes minus E times the electric field vector. So you can see this is a vector equation. One vector is opposite to the other vector because of this negative sign. So that's why if the electric field is in one direction, the force acting on an electron is in the opposite direction. So now we can calculate the magnitude. Let's first calculate the magnitude because we know the direction of the acceleration. It's the direction of the force acting on the charged particle. So this is the direction of the acceleration is also in that direction from Newton's second law. If there's a net force acting in one direction, that's the direction of the acceleration. So we know the direction of the acceleration now, but let's try to figure out the magnitude of the acceleration. So magnitude of the acceleration from Newton's second law, I can write this expression, specifically substituting for the electron. The magnitude of the acceleration is equal to electrostatic force, magnitude of that, divided by the mass of the electron. Now the magnitude of the force, electrostatic force, is given by this expression. We simply take the magnitude of this one. So then E times the magnitude of the electric field divided by the mass of the electron. So now you'll get that the magnitude of the acceleration is equal to 1.6 times 10 to the power minus 19 coulombs times the electric field 570 newtons per coulombs divided by the mass of the electron, which is 9.1 times 10 to the power minus 31 kilograms. Now I'm not going to put the units for each term. I'm finally going to put over here that the units is meters per second squared. Now when we solve this, you will see that we'll get 1.0 times 10 to the power 14 meters per second squared. So that's the magnitude of the acceleration, and if we consider the direction, we can write this as plus 1.0 times 10 to the power 14 meters per second squared, and I can write j hat, saying the unit vector in the upward direction. So that means I'm defining j hat along the positive y direction. So this is j hat vector, and that is in this direction, in the positive y direction. Okay, so that's why I expressed it in terms of unit vector notation. So this is the answer for the first part. We get the acceleration in its unit vector form. We know the direction of the acceleration, and also we know its magnitude. Okay, now let's look at part B of this problem. It says determine the time of travel for the electron through the electric field. So the electron is inserted at this point. So this is the start point for the electron, and it goes in this curved path because now it has an acceleration in the upward direction as we showed in part A. However, now we want to find the time of travel for the particle, for the electron, from here to here. Okay, so how are we going to do that? So let's look at that one. So part B, the electric field is downward. So that's the electric field. And then the electron here has a horizontal velocity of 7.0 times 10 to the power 6 meters per second, but there's an acceleration acting perpendicular to the direction of velocity. So let me show that acceleration in a different color. So this is the direction of acceleration now. Now from general physics 1, you should realize that this is similar to horizontal projectile motion, right? If you recall, like projectile motion, let's say that you have some sort of a building, and you have an object here. You project a particle in the horizontal direction, and as a result, what's going to happen is that since gravity is vertically downward, like that, in that direction, the particle goes like this in a curved path. So that's the path of the particle. So that's the same thing that happens over here. This is from general physics 1. Okay, so that's the same thing happening here. Because the acceleration is upward, what's going to happen is that the particle is going to curve up like this. So this electric field, uniform electric field, is doing the same thing that the gravitational field is doing when we study general physics 1. Okay, so with that, what I'm going to do is that I'm going to apply kinematic equations. So remember, just like here, if you recall, the horizontal velocity does not change. It's the same value. What happens is that the vertical velocity is going to increase because gravity is acting in that direction. So vertically, the speed is going to increase. Horizontally, nothing is going to change. So an important point here is that since the acceleration, since a vector is perpendicular, so this symbol stands for perpendicular to the speed or velocity, horizontal velocity the horizontal part, velocity will not change. Okay, so as a result, we can apply this expression delta x in the horizontal direction equals v naught x t plus 1/2 at squared in the horizontal direction. Delta x is the separation in the horizontal direction, and it's given in the problem. This distance between the start point and the end point, if you recall, that was given as 0.35 meters. So we have 0.35. V initial in the x direction is the 7 times 10 to the power 6, because that's not going to change. That will be the same value at all points. 7.0 times 10 to the power 6 meters per second over here. Over here it will be the same value. The horizontal component does not change. Only the vertical component increases because there's an acceleration in that direction. That's the reason. Okay. So then we have 7.0 times 10 to the power 6, and we want to find the time. This part is 0 because the acceleration in the horizontal direction is 0. That's why. Since no acceleration, no a in the horizontal direction, that's why it's 0. Okay, now we can simply solve for time. You'll see 0.35 over 7.0 times 10 to the power 6 seconds, and the time you will see that this is going to be 5.0 times 10 to the power minus 8 seconds. Okay, so that's your that's the answer for part B. It's very straightforward. You just need to remember your knowledge in kinematics in solving these projectile motion type problems. So that's the only thing that you need to remember. So I'll write this down correctly, like more clearly, 10 to the power minus 8 seconds. That's how you do this part. Okay, now let's look at part C. In part C, it's asking determine the angle the electron makes with the horizontal as it emerges from the other side of the electric field. So that means at this point, now the electron is going to curve because the acceleration is in the upward direction, and at this point we want to figure out what is this angle. So how are we going to do that? So this is the method to solve for part C, that is how to find this angle alpha. If you can see, I have enlarged this region over here. This is the electron and this is its horizontal velocity or the speed, and you know the horizontal component does not change. Why is that? Again, remember, the acceleration is perpendicular to the horizontal direction. That's why the horizontal component does not change. So this does not change. This does not change, and we already know that value. VH is equal to 7.0 times 10 to the power 6 meters per second. But then the vertical component at this point, at the point of ejection, there's going to be a vertical component of speed. Why is that? Because the acceleration is applied in that direction. So here at the beginning you start with a 0 vertical component for the speed, but at the ejection point there's going to be a non-zero value for the vertical component, and we need to find that. So how are we going to do that? we can apply for the electron in this direction. We can apply in the upward direction V equals V naught y plus a t. This is also a kinematic equation from General Physics 1. So this is the final velocity. So I'm going to call it like V, the final speed in that direction, V vertical component. And this is, we already know it's 0, right? Because there's no vertical component at the beginning of the motion because it's completely horizontal. So that's why I'm going to put a 0. And then plus a, what is the value for a? That's over here, and we figured that out. So if you recall that was this value. 1 times 10 to the power 14 meters per second. That's the magnitude of that. It's pointing upward. So then 1.0 times 10 to the power 14 is the acceleration, and the time we figured that also. We got the time as 5 times 10 to the power minus 8. So the time does not change, right? So when the particle moves from this point to this point, it takes 5 times 10 to the power minus 8 seconds. That's for the horizontal motion. During that time, the electron is moving under this acceleration in the vertical direction. So during that time, it's going to move this direction. You can see there's a direction, and that's moved because there's a velocity component, a speed in that direction. Okay, and that's what we are trying to figure out. So we get 5.0 times 10 to the power minus 8. So then finally, we will get this answer as 5.0 times 10 to the power 6 meters per second. So that's the velocity component in the vertical direction. Then finally, we can find alpha. We can use trigonometry, right? So tangent of alpha is equal to, you can see the opposite side over the adjacent side. So V over VH. And then we get 5.0 times 10 to the power 6 over 7.0 times 10 to the power 6. So this will yield alpha equals inverse tangent 5 over 7, and that's approximately equal to 35.5. So up to 2 sig figs. So then this would be 36. Alpha is 36. So that's how you do this problem.